In today's session, Dr. Mike, to present to share project on optimization, statistical answer to
Thank you, madam. Thank you. So, good morning, all of you, dear colleagues. Today, I am going to give a lecture on optimization through a statistical response surface methods. So, I am Dr. Malaya, Associate Professor in Chemical Engineering Department. So, first of all, what is a response surface methodology? So, there are many factors will be existed once the process is we have to conduct in any physical unit operation. So, in that factors you cannot you cannot get which factor is more impact on the particular yield or conversion of a product. So it is in the terminology of the any chemical process or the biological process. Okay. So in that case, some kind of the biological process, there are maybe 11 factors are there, so which influence on the yield of the product. So in that case, this uh, response surface methodology, so this is useful to optimize the factors which are more influencing on the process. So now we have to see what is a response surface methodology. It is especially a mathematical tool. So the collection of the mathematical as well as the statistical techniques that can be useful for modeling and analysis of the chemical as well as any other process. So why I am telling this chemical means, if you go to any industry, so there are a lot of industries are involved with the chemical process. So along with that chemical, you can say that some biological process or the pharmaceutical product process. So in that case, there are the lot of the factors that influence the yield of the process. Okay. So in that case, this especially the RSM is useful. So how can you optimize the yield? So that means, if you give any input, so that input is you can find the how much of the output you are getting. So output is the function of the input variables. So that is why the output is influenced by several independent variables. So the objective is here to optimize those parameters to get the yield or the conversion of a particular product. So this is the simple definition of the response method. So now you know why we have to optimize the process. Exactly what is a optimization? So optimization, please remember, it is a optimization. It may be a process or methodology or the act. So you can optimize the process or you can optimize your method. So if you take any product, any process, so out of that, suppose if you want to produce any chemical compound, like the example is the sulfuric acid. So here you can manufacture the sulfuric acid by different process. So especially there are two process are existed. Out of that two process, which process is feasible? Okay, so that is what we have to study. So that's why the optimization defines it is a act or process or methodology. So making something, so whether it is the design or you have to select a system, or you have to decide, you have to give a decision in terms of the process or the design variables. So it is a fully perfect functional. So once you design the equipment, so for a particular process, you have to decide so which how much of the conversion or yield you want to choose. So that should be perfect, and that should be we have to design specifically in the mathematical procedure. So means you are allowing the some physical system, physical process in terms of the mathematical expression. So those mathematical expression you have to solve, means you have to scale up for any kind of the levels. So that is what the optimization defined. So here ultimate goal of this optimization is, means what is the characteristics of the optimization process is, you have to choose the best one among the all the interaction parameters. As I said, in the biological process there are almost 10 to 11 parameters are initially 10
involved
to
to
11
get
parameters
the
are high amount of the yield or the conversion of the process. Among that 11 process, you have to choose the best interaction parameters. So that is the optimization gives. So let us see what are the parameters. Those are those are giving the major influence on the yield of the product. So let us see what is optimization parameters. As I said, you have to select the parameters like you have to select the parameters like, let us say I have the process, in that I have to choose the parameters 2 or 3. So you have to identify which parameter is influencing, means identification of the factors. So how many factors are there? Let us say all of you know the if you take any chemical
excuse
process, let us say, yeah,
excuse sir, can you please on the slideshow? Slideshow.
slideshow.
Yes, sir. Okay, sir. Okay. No issue,
Now
sir.
is
Thank
it
you.
okay?
It's visible, sir. If slideshow would be there, that would be much better. That's what we thought. It's okay, sir.
It's okay now.
Yeah, okay, sir.
Okay, right.
You can continue, sir. I've seen it. Sunita ma'am, do you want to speak something? You have raised hand, no?
Only half of the slide is seen. Please ask the sir to go with the slideshow.
Continue, sir. Malay, sir, you can continue the class.
Yeah, yeah. Now it is okay. Sir, now it is in slideshow. Hello, sir.
Yes, sir.
Is it
Now it's
visible?
visible.
Huh?
It's visible now.
Right, right. So here the in the optimization, yeah, my voice is yeah.
Sir, it's audible, sir.
Yeah, yeah.
It's audible.
So here, what is the optimization? So in the optimization, let us say if you consider 2 or 3 parameters. So let us say in any process, let us say the temperature or the pH or the concentration of any of the reactant. So in that case, I can take 3 parameters or 2 parameters, whether the temperature or the pH. So in that case, you have to identify the process, which are the major factors that influence the yield or the conversion of the process. So that means the factors which define the process property you have to identify. Then after identifying the factors, then what we have to see, so let us say if I selected 2 or 3 parameters, it's not a problem to conduct the experiment because suppose if you consider the 2 factorial design, so it is 2 square or 2 power 3. If it is 3 parameters, then 2 power 3 is 8, so you can conduct the 8 experiments. But if it is a biological process which contains more than 10 parameters, let us say it is 10 parameters 2 power 10, so it's almost huge number. So huge number of experiments we have to conduct. Then it is difficult to conduct such a huge number of experiments. So in that case, we have to screen the factors. So screening is identifying the most influencing factors. So after screening the parameters out of 11, let us say for example 11 parameters, your process yield only have influenced by only 4 or 5 parameters, then you can go ahead with all these experimentation. It's around 50 to 60 experiments. So then it is easy to conduct the experiment. So in that case, you have to go for the screening of the factors before going to actual optimization process. So that means screening of the parameters, it can be done by some of the techniques which are existed. So we will see later. So after that, you have to, after screening the factors, then you have to go for the response surface methodology. So in that there are many types of the response surface methods are there. So after that, central composite design is the best one. So which will give the exact model what we want to establish. So that kind of model we can get from the central composite design. So after screening the parameters, you have to go for the optimization with using the response surface method. So finally, you have to optimize your process. So by going this sequence of the steps. So now what is the model? So as I said, so if you want to build up a model, so there are certain inputs are there. So let us consider a dependent variable. So let us say y is the dependent variable. So and there are a set of input variables like x. So the x may be x1, x2 up to xn or xk. So here you have to define your model. You have to define your model. So in terms of the dependent variable, so y is a function of the x. Y is a function of the x. So for example, here I am considering y is the viscosity. So viscosity of a polymer. So which might be the function of the x1, x2, x3 variables. So those x1, x2, x3 are the reaction time, temperature, and the catalyst feed rate in the process. So three variables. So three variables are inputs. So x1, x2, x3 are the temperature and time and the catalyst feed rate. So I have defined the dependent variable y as a function of the x1. So in that case, you have to give a linear equation or non-linear equation. Obviously, you can go for the linear equation. Let us say y equal to x1 plus x2 plus x3. So that is a linear equation. But here, in certain cases, any physical process that may not be follows the linear relation. So in that case, you have to design, you have to model the equation such a way that all the interaction parameters, whether it is individual as well as the combination of all these factors. So that is the main idea of to establish a model. So when the model is fully understood, then you have to do the experiment. After experimentation, so after fitting the model, so whatever the model you have fitted, then you have to test that fitted model with the experimentation. So in sometimes whatever the fitted model is not giving the exact results, means it is showing some error. So in that case, I am adding one more factor, that is the error. So how much of the error should be added? So those kind of things you have to need to develop a model. So here How to generate a model? So first, you are assuming that y equal to function of x1, x2, xa, xk plus some error. But how can you generate a model? So obviously we can use the design of experiment, then multiple linear regression technique, multiple linear. So you know the linear equation. Let us say y equal to mx, it is linear. Y equal to mx plus c, it is also linear. But y equal to mx square plus c into x plus d, where c and d are the constant, then it is a regression model, means it is a second order equation, second order polynomial equation. So you have to develop a model for a particular system by correlating these expressions. So that is the your objective of this model. Then after a regression model is established, then you have to test the response surface plot. So you know this is a the empirical model, so which gives the response surface method. So here see the diagrams. There are two plots. Left side it is the bivariate. So you know y equal to x axis. Y is defined as mx plus c. Y equal to mx plus c. You know all of you know it is a simple linear equation which has the constancy. And if you see the right side, there is a multivariate. So this is the response. What are the surface diagram it is given? It is the response which has the number of experiments. These dotted points are the showing the number of the experimental outcomes. So you know it is the xyz. So means multivariable. So at a time you can vary two or three variables, then you can find this your objective. So it is defined. So this multivariable is defined by this equation y is equal to beta naught plus beta 1 into x1, beta 2 into x2 plus beta 1 2 into x1 x2, where beta naught, beta 1, beta 2 or beta 1 2 are the constant, x1 x2 are the variables. So that means x1 x2 are the inputs and y is the output. So now I am taking only the two variables. So suppose if it is a two variable, obviously you will get the quadratic equation. So y equal to beta naught plus some constant into x1 x2. So suppose if it is a two parameters, then you can find this expression. Suppose if it is a more than 3 2 3 4 5, then you have to add beta 3 into x3 plus beta 1 2 are already over, then beta 1 3 x1 into x3 plus beta 21 x2 into x1. So like that, so some other parameters should be added. So you have to account all these interaction parameters. Now what exactly response surface plots gives? So if you see here left side, as we discussed now, it is a multivariable. So there are two factors. The response is here shown, response versus the two factors here. It is the surface diagram. So it is the graphical representation. So in the graphical representation, it will give exactly what is the maximum value of the factor 1 and the factor 2. At what values of the factor 1 and factor 2, your response will be maximum or your response will be minimum. So those kind of things you can graphically observe. So this is the graphical representation. So in terms of the three-dimensional picture. So if you see the right side of this diagram, this is the contour plot. So it is in the two-dimensional picture. So x and y. So there are factor 1 and factor 2. So inside you can see the design space. So where exactly this optimum values of the factor 1 and factor 2 you will get. So that will be observed by the contour plot. It is a two-dimensional picture or the three-dimensional picture response plot. So you can use any one of these two. So to find the optimum parameter. So here some types of the response surface graphs. So first A, B, C are there. A represents surface with a maximum point. So here if you see y cap as a function of the x1, x2 and so on. So if you see here, this is the maximum point obtained. So for corresponding x1, x2 values, corresponding input values. So this is the exactly reverse of the above one, which shows the minimum point. So at what level? So minimum means, so when is the minimum optimization is required? So generally, if you go for the cost considerations, so if you want to design a particular equipment, you have to optimize your cost. You have to minimize the cost. So optimize means you are going to optimize the parameters by maximization of the yield or conversion or the minimization of the cost. So these kind of the plots, those are helpful in the especially design of the equipment corresponding to the cost consideration. And the third one is the saddle point, so which shows so how it is deviating. So minima to maximum. So the third one is minimum to the maximum. So where exactly the process is deviating. So these three are the major surface diagrams which can be existed in the process. So there are the statistical methods, response surface methodology, as I said, central composite design or bracket permanent design, or the design of two factorial design, or some other methods are existed. So in that case, how could you say that the model is fitted well? So in that, you have to define the model, exactly whether the model is fitted to the experimental data or not. So here first we have to run the experimental runs, then validation of the model can be done by the experimental data. So that is by testing these statistical tools like p-value, r-square value and f-value. So if you know this, then you can find that your model is good. Your model is good, or your model again needs to be further refined. Means you have to use your linear regression model or non-linear means polynomial model. So what kind of the response you are getting? So that depends on the method you have to, what method we have to select it. Based on that method only you can find whether the model is good or not. So in that case, first remember p-value, you have to test the p-value, then r-square value. So many of you know only the r-square values, I think. So all of you know, but thing is, if you plot a graph x and y, x versus y. So x-axis, y equal to function of the x. So if you plot a line, so if it is getting with 100% correlation, means linear relation, then you will get r square value is 1. So y equal to x. Suppose if it is a y equal to x square, so can you fit the same data? So I have the data x versus y. Now it is following the linear relation. Now I want to correlate y equal to x square. So can we fit the same data for this equation? So we cannot fit that data because it is almost non-linear relation. Yeah.
Sir, we are still in this optimization slide, sir. Fourth slide. Are you taking the same slide, sir? Fourth slide only, no, sir. You are
statistical
you
method.
Have you changed the slide, sir? Because we haven't changed. Slide wasn't changed yet. It is still in the fourth slide.
So
which
this
slide
is
number are you taking?
Yeah. So this is the problem is happened with the slideshow, sir.
Okay.
So now it is showing only optimization.
Yes, sir. Yes, sir.
Yeah, that is what initially what I told now. So for scrolling, now is it visible?
Yes, sir. Model slide number 5, sir. Now.
Yeah. So this is the problem, sir. This is the problem.
So thank you, sir.
So can I repeat the same thing, sir? So this is the model as we discussed now.
Sir,
Y equal to
repeat, sir. Because
Yeah.
now you have shown the slide. Can you please repeat? Because I was thinking it is only the first slide what you were explaining.
Okay, madam. But thing is, here I found some drawbacks are there. So if it is a slideshow mode, then the slide
Actually, you are
won't
not
change.
in slideshow mode, sir. You are not in slideshow mode. Your slides are there to the left side and only the middle slide you are scrolling. If you can go to the slideshow, custom slideshow, you have to click custom slideshow. Then you will go to the slideshow, sir.
Custom slideshow.
Yes, sir. Then you say from current slide, at least. You can tell from current slide. You can click the current slide.
Yeah.
Yeah.
Now, can you see this next slide, madam?
No, sir. You are still on the same one.
You're on the slide model. The slide number is 5, sir.
Yeah.
Model. That is what you are speaking about, sir.
Yeah, this is what I'm going to explain. Yeah. Now, what madam is saying, you have to click the custom slideshow.
Sir, you can even go to from current slide also you can tell, sir. Generally, this is how you have to tell, sir. Normally, you will have these things, no, sir. Design, if you, yeah, when you go to your slideshow, okay, from beginning you can say or from custom, that also directly you will get that, sir. From current slide, you can say that current slide. So directly your current slide will be coming in a full screen. From current.
Yeah.
Yes, the next one, adjacent, yes. Click that one, sir. Did you click?
Yeah. Next slide, is it coming, madam?
No, sir. It has not come. Okay, sir, you continue like this. So you have to scroll each slide. Now you have gone to the next slide. Yes, okay, you can continue. That's okay, fine. If there is a problem, you can please continue like this only, sir.
Yeah, now it is feasible? Yeah.
Sir. Now it is very clear, sir.
Yeah.
Right, thank you. Right.
Okay, thank you. So now if you want to model a process, then as we discussed now, consider the dependent variable y. So y is the dependent variable. And now I want to give some input variables like independent variable. So here input variables are the independent variable. Now y is the dependent variable. So for example, if I am considering y might be the viscosity of a polymer. Sir. No, what madam is saying?
Slide show. ఇది నొక్కండి సార్. ఇది నొక్కండి. దాని పక్క సార్, అది కాదు. స్లైడ్ షో. స్లైడ్ షో.
Madam, these slides are changing or not?
All the slides are there, sir. Now you have to click the slide, the current slide, and then go ahead. Now what you have done previously is the right one. Where we can see only individual slides, sir. Now the one which you have highlighted, orange one you can see, no, sir, highlighted. You please click that and then continue.
Madam, now just I am going for next slide. Is it visible?
No, sir, I can see all the slides.
Okay. Right.
Yes, now you are in the single slide.
Right.
Slide.
Yeah. Now next.
Slide, sir.
Next slide.
No, you are on the same slide, model slide.
Okay. No
Consider any dependent variable and input variable.
There is a problem with this, madam, because I am using XP pen. Okay.
You continue, sir. No,
Yeah. Thank you, madam.
Yes.
So now y is the independent variable. Then x is a y is the dependent variable and x is the independent variable. Let us say y is the viscosity, which depends on the reaction time and the temperature and the feed flow rate of the catalyst. So in that case, we have to design the model whether it is linear or the non-linear. So based on the experimentation only, you can say that the model is linear or the non-linear. So now see here the equation I am defining y is equal to function of x1, x2 and so on xk. Now let us say y equal to function of x1, x2, x3. So if I write in the linear